Mike. I appreciate the dedication.
Okay, so welcome back. We'll get a nice break. We're going to continue talking about distributions of two or more variables together, and the aspect that we're looking at is conditional expectation, conditional variance. So the expectation of a conditional distribution. What is it? How do we use it? And then how does it get used in things like Bayesian analysis? How does it get used in some hierarchical models, right? So kind of the first thing to note is conditioning is very important. It applies statistics really. So it's really an important tool, but it's also really an important mindset for thinking about what information do you have, and how does the information you have change the probabilities. So there's an article that was in today's, maybe USA Today, but also Burlington Free Press, looking at rates of episiotomy, so surgical cuts made during birth to help babies get out of the birth canal. And it says that back in the 1970s, it was a very common procedure. They thought it was really helpful to avoid worse tears and other damage from a large baby being born. And it was done 20, 30, 40% of the time in births that were not C-sections. And so USA Today has been researching, gathering data from hundreds and hundreds of hospitals on this. The rates now are much lower. Right? There's evidence is accumulating that it's not necessarily so helpful, and other techniques can help this. But a comment in the article says, yes, but so far the analysis hasn't adjusted for the patient case mix and the different conditions of the women. That so far the analysis hasn't conditioned on the fact that different hospitals are treating different types of women in different conditions, with different backgrounds, different levels of prenatal care. And so until they do that, the analysis won't really be conclusive. Right? So until they do conditioning on other pieces of information that are known to affect the outcomes, there's still going to be, people are going to say, well, you haven't quite really explored it to the full extent that it has. So conditioning for big analyses, for small analyses, is quite important. It shows up all the time in studies. So we're going to look at kind of three aspects of this. Right? What is conditional expectation? How can we compute it for a couple times? We're going to look at the relation to marginal expectation. There's two relationships that are really useful in statistics, I find, in thinking about computing harder expectations, and in modeling data, and thinking about variability in data. And then we'll do something with Bayes calculations. Bayes rule, but applied to that. It's kind of an extension out of the second one, really. 6.8 in the book has a small section that's related to this, something called compounding. Convolution or compounding. So it's kind of a similar idea that's out there. We probably won't talk about that separately, but it's along the lines of these things, right? So conditional expectation, right, begins with the conditional densities or conditional probabilities. Right? So kind of definitional type of things. If we have a joint density of two random variables, f of x and y, on two variables. If these are continuous, we can get the marginal distribution of one of these. Say we get f of y. What we're going to, is that how I wrote it, right? We would get that by integrating the density and integrating out the x's, treating x as a random variable and averaging over all the values that could be there, essentially integrating out, and we get the marginal density of y by itself. Then the conditional density of x given y, given that y equals a certain value, is x, this line given y, is the joint density of these divided by the marginal. And we can apply that to any of these examples where we give it little x's and y's, some formula, integrate out one, take the ratio, and that's the conditional density. And so this density of x is the random variable here, and y is the thing that's given. And so this can be a function of y can still appear in this, right? Y can appear in the numerator, y can appear here, and so the y's might not cancel out. So the distribution of x could change as you get different values of y, right? So if y is related to age, as age of the mothers is going, and x is some quantitative health measure, blood pressure or some other health outcome, or some pain threshold, right? That depending on what y is, the distribution of x can be changing. So we could be, on average, getting bigger or getting smaller. It can have more or less variability depending on what y is, but the distribution can be changing, right? So in this, then we're going to calculate the expectation of x, right? So the conditional expectation of x, conditional expectation of x given that y equals a certain number is written as the expectation of x given that y is some value, and it's going to be integral of x in the continuous case, so taking expectation of x, but then we just use a conditional density of x given y dx. And whatever value y is might still show up in this expectation, that the average value of x could be related to y, and we haven't integrated out. It could still have some role there, and as y is changing, then these expectations could be changing. Right? So let's do one type of ordinary example like that, like this. So let's say f of x, y, the density, and this particular density is 6/5 x squared plus y, and the x and y are both between 0 and 1, and they don't restrict each other. Right? We know by factorization this thing doesn't factor into an x part times a y part. So by factorization theorem that we talked about, right, x and y are not independent. Because you can't factor it into an x thing times a y thing. They aren't separable in that to produce that equation. We know right away that they're not independent. That's kind of just a side, but something good to know. Right, if we want to do the margin of y, we're going to integrate out x. X goes from 0 to 1, so there's a 6/5 x squared plus y, and we integrate out x. So that 6/5 can be pulled out. And then with respect to x, right, this one's x cubed over 3 plus y times x, and evaluated from x going from 0 to 1. And so it's 6/5 times 1/3 plus y, and then x is 0, so that's gone. Right, so that's the marginal density of y. I guess you could multiply through by 6, and so there's a 1/5, so there's a 2 plus 6y. Is a little simpler way to write it. This is good for the values of y, 0 and 1. Right? So then we could find the conditional density of x given y. And f of x given y, that conditional density, is just the joint over the margins. And so I guess it's not much, this is a simpler form of that, but looking at this one, x squared plus y is here, and then 1/3 plus y is here, and maybe you would simplify that, multiply by 3 on both sides, so we don't have a, so 1 plus 3y, right? And that's for x's, right, between 0 and 1. Right? So in this case, the conditional distribution of x does depend on what y was. So as for different values of y, you will get different densities of x. Yeah.
Why'd you get rid of the 6/5?
Well, the 6/5 was up here and it's down here, so when I put this one over this one, they just cancel.
But like for the bottom part?
This part, so I had a 6/5 here
Yeah.
in just the margin, and I also had a 6/5 originally in the density. So when I wrote the ratio of those two things just
okay.
canceled. So, y is a number there. So if you give me a number of y, say, let's say y is 1/3, then the density of x, given that y equals 1/3, is you would plug in, x squared plus y is going to be 1/3, and this is 1 plus 1, so 3x squared plus 1 over 2. Right? So that's the specific density when y equals 1/3 in this particular distribution. Right? If you give me a different value of y, it's going to change, right? And it's going to favor different values of x. Is it going to be more concentrated toward 1? This density, this function is increasing. It gets higher as x gets bigger, right? And it's smaller as x gets smaller. So it's going to have more probability towards the larger values. Right? Now, conditional, yes.
So in terms of the hospital example,
Yeah.
the goal of conditioning the data is like to combine, for example, all the women who are older than 35 or something like that.
Well, so if certain hospitals tended to treat older women or more at-risk pregnancies, say, or if women who had previous problems tend to go to certain hospitals, so they get more cases where certain treatment, or and part of it's then if you wanted to compare hospitals and say, okay, well, this hospital is doing the most, this is doing the least, is that simple rate of doing the procedure really comparable across hospitals, right? So if one hospital has a patient population that's more likely to need additional care or additional procedures or have difficulties, then they're maybe more likely to get certain things anyway. So conditioning would kind of adjust for that. In other hospitals, when they rank hospitals in terms of other things, like what is the cure, what is the survival rate for people who have heart attacks if that go to a hospital. Well, if some hospitals are further away, maybe there's less chance that an ambulance can get to them quickly and help them. So if their survival rate is less, are they really doing a bad job? Well, you might want to take into account that they have different circumstances. Instead of being very close to all their population, if it's very far away, and they have to travel more, they might be doing worse, not because their care is worse, but because of other factors. Or if their population of patients tends to be older, or more obese, or heavier smokers, and they have more, a higher death rate, are they really providing insufficient care in comparison to other ones, or is it because of that patient population mix? So the analyses kind of adjust for that. Yeah, yeah.
I don't really understand how you get the density function for y in that denominator.
In the denominator over here, so taking the, to get the marginal one here, right, this is the joint one, the f of xy, and we just simply integrate out x.
Okay. But
And then this is kind of related to the marginal, the joint had a 6/5 here, and this one way of writing it had a 6/5 here. And I didn't write it down, but I just kind of canceled those two things from that. Did I? Did that help a little?
yeah.
But anyway, they're different. So now, conditional expectation would be the average value of x. The expectation of x given. Y would be the integral of this thing. Now x go from 0 to 1. The conditional density was 3x squared plus y over 1 plus 3y. That's projected x. So there's 1 over 3, 1 plus 3y doesn't depend on x, so that's kind of like a constant that's there. And then there's also that 3 can come out. So then there's an x squared multiplied by x times x cubed, so there's an x to the 4th over 4. Right? And then there's x times y, so there's a y, x squared over 2. And then x goes from 0 to 1. And so there's a 3 over 1 plus 3y. And then there's 1, so there's 1/4 plus y over 2. Right? That's the conditional expectation. Right? It looks, y is still there because the distribution of x changes depending on what information you get from y. Right? And so if we had that example where y is 1/3, then the expectation becomes a specific value by plugging that in. So there's 3, if that's 1/3, then that's 1, so there's 3/2 here, and there's 1/4 plus, if that's 1/3, then it's 1 over 6. And whatever that actually ends up being, and do it, right, 3/2, put everything over 12ths, then there's 3 plus 2, so it looks like it's a 5. It's going to be up here in the numerator. You can cancel that. So it'd be like 5/8. It'd be a little bit bigger than 1/2 because the conditional density tended to favor higher ones, right? So that's kind of a mechanics of how this works. Right? And so you can do that with these little examples, right? But one other thing, but any questions about? You could also do a variance calculation using that conditional density, but we're going to move on to look at this relationship to marginal. Right? So the second kind of thing here is the relationship of marginal conditional expectation. So if we just have a random variable y, what's the expectation of y? Well, we only have one value, and they're continuous. We take an integral of y, and then times its density, and integrate, and that's that. If we have two variables, right, we can write down the expectation for a function of x and y, in this case just the y, with a double integral. It's going to be a double integral of y times the joint density of x and y, and then we integrate out y and then x. You could do x and then y and x, but what we're going to look at, it's nice to have the y on the inside. Right? That's also the expectation, right, of y. Right? over jointly the distributions of x and y together. We can do a little manipulation with this one. So inside here, this joint density, so if the conditional distribution of x given y, is that the one I want? No, I want y given x. Is the density of both of them over the marginal of x. And so it's kind of not exactly how I did it before, but we're going to want it over x to make this work out, right? If that's a conditional density, that means that if we write f of x, y equals something, it can be, multiply both sides by the denominator here, and it's going to be the marginal of x times the conditional density. So that the joint density is equal to 1 times the conditional density, just like a joint probability of two events can be thought of as a probability of 1 times the conditional probability of the second given the first. Right? And so we put that in there. That's an f of x, f of y. You could put subscripts on that, but I'm just going to use that dy dx. Now, this first inner one, right, has y as this active argument. Right? So the things that involve just y have to stay inside that. They can't be pulled out. But things that don't involve y, like f of x, there's the marginal of x, there's no y function in there. We've integrated y completely out of it. It's gone. And so this thing can be regrouped a little bit. Where we have y, f of y given x, dy in here. And then on the outside of that, we can have the marginal of x. So we have the joint density, then we wrote it as the marginal of 1 times a conditional, and then we realized that if there's dy here, the things that are x alone can be separate from that. What's that inner thing? This integral with respect to y of y times the conditional density, that's a conditional expectation. That's the conditional expectation of y given x. So this inside here is a conditional expectation. But we're integrating that thing over the density of x. Right? So we're taking the expectation of a conditional expectation. So this is some function. We can think about it. You can think about it as a function of x. As x changes, you're going to get different expectations. So this thing is the expectation of y given x. So it's an expectation of a conditional expectation. And remember where we started is just the marginal expectation of y. So the expectation of y can be written as the expectation of a conditional expectation. Right. And so that's a first relationship, right? Relating the marginal to a conditional. So where would we use something like this? Well, let's look at any question about the integral? So let's say that we have a relationship, that we have some variable y that's related to x. To some equation. This is the usual linear type equation. That's used in normal linear regression. And what this says is that y has a linear relationship with x. So here's x and here's y. So there's this slope, this line that says as x changes, how does y change? And if it's linear and increasing, it would be like that. This little epsilon added onto there is a little normal error. So it says the points we'd actually see, the actual data points, are going to be somewhere around that line. They're not exactly going to be on that line, but it's going to be on that line plus some random error. Right? And what's the distribution of that error? That error is centered around 0. It has some variance, right? Because in every problem you're working on, the scale of y has some spread to it, but it's roughly normal. So it's going to be near 0, plus or minus a couple standard deviations around there. So that's the ordinary linear regression model. What this model implies is that an expectation of y given a value of x is alpha plus beta x. Right? So it's a function of x. The average value of y is increasing, since I made it a positive slope, is increasing in that linear way. So as your income goes up, maybe your expenditure on something is also going up in a range. Right? Or as the weight of a negative relationship, maybe as the weight of a car goes up, if beta were negative, then the miles per gallon would be going down. So there'd be this change. Well, now if x has a distribution, that x has some distribution, say that it's has a mean and a variance as well. So under these two stipulations, the distribution of x and a conditional distribution of conditional assumptions about y, what's the average value of y? Well, our relationship that we had before now is useful because we want this marginal expectation of y. We have a conditional expectation and then information about the average value of x. Right? So the average value of y by this relationship is this conditional relationship. So the average value of y, the average value of y conditional on x is alpha plus beta x, where alpha and beta are numbers. Expectation is a linear operator, so we can pull through these things. And if mu sub x is the average value of x, then the average value of y is going to be alpha plus beta times that. It's going to be determined by that line. We'll put a few numbers in there, right? So let's say y is concrete numbers in here, 80 plus 10 times x plus some error. And let's say the error is a normal random variable distributed with mean 0 and variance 50 squared, so standard deviation of 50. And x itself is distributed as a normal random variable centered at 35 with a standard deviation of 10 squared. What is the average value? What is the expectation of y? The average value of y? Well, our equation would say that the expected value of y is the expected value of y to an x. So that's this part is the expectation, right? 80 plus 10x. And so 80 plus 10, the expectation of x, is centered at 35. So we have 80 plus 350, or 430 as an average value of x. What is this? We're also going to be interested in the variance. That's going to be a second relationship. We can do a little simulation, right, to generate some data that would look like something we would get out of this model. This was the, well, that's starting up. So let's say that we're going to generate, say, 40 points. And X random normals centered at 35. We need 40 of them with a mean of 35 and a standard deviation of 10 we said, right? So here's my X values. My random sample seems to be a little bit skewed, you know, but with small sample sizes you can easily get a few that are out of there, right? Now Y is supposed to be, I said in this one, you know, 80 plus 10 times X. That's just the, right, so if you plot X versus Y, that's just the line part of it, right? The actual value of Y has some random normal noise about it. So again, endpoint centered at 0, and I said a standard deviation of 50. So now if you plot X and Y together, that's the scatter that's implied by those equations, right? It's just one sample of how that would look, right? So if you had something that you plotted X versus Y and thought it was a linear relationship, that, you know, this would be kind of what it would show up, right? The average value of Y, you know, here's the values of Y by themselves, just the margin of Y. And the mean of the Y values in the simulation is 448. My theory said it would be 430, but it's kind of a small sample size with some variability. So it's not exactly that, but it's, you know, it's not too bad. You know, we put a vertical line at the mean and make it, you know, red so it shows, oops. That's going to be, right, so there's the average of these. And so the 430 is back over here. Well, 448 is the average in this particular sample. There's a little, and a few more big points, big X's, a few more bigger Y's than typical. But that's what's implied. And so the probability theory says the average for random samples would be 430. If we took very large samples, 400, 4,000, 4 million points, the average would be quite close to that 430 theory point, right? So this relationship is our first one, right? But any questions about that? So remember how we got it was by looking, you know, writing first the expectation of Y with respect to the joint density, and then breaking it into a marginal and a conditional, and kind of working through that it worked out that way. The second relationship is about variance, right? What is the variance of Y? Right? Well, if you write it as that joint density and get things squared and multiply things out, it turns out that you can write it as the expectation of the conditional variance plus the variance of a conditional expectation. That it has two parts, right? And so there's a little bit of extra, you know, it's not just taking the conditional variance and taking expectation of that, but this other thing, you know, the Y, the distribution of Y changes with X, so the means are changing, so there's kind of two parts to it that are there. So in this example, we had that Y was alpha plus beta X plus this, so the expected value of Y given X is alpha plus beta X. The variance of Y given X. So given X, this is just a value, given something filled in here. So the variable is all in this thing here. So the variance in this case is this, just related to the normal random error about the line. So this is the expectation of the variance, this conditional variance is sigma squared epsilon. This expectation part is this linear part, so alpha plus beta X. Now we're taking expectation with respect to x, expectation or variance there. This part, that's just constant, right? So sigma squared e, that's just a number, it doesn't change. The alpha, that's just a number, that also doesn't affect variance. And beta is a multiplier there, beta squared comes out and gives the variance of x. So it's sigma squared epsilon plus the beta squared times the variance of x. That's what it ends up being when we apply it in this case. So in terms of the numbers we used, this thing was 50 squared in the example. Beta was 10. And this variance of sigma squared x was also 10. So it's 2,500. 100 times 100 is 10,000. So the variance of y is 12,500. To put that on a scale, take the square root of it, it puts it more on a scale that's, that's the y dimension. We take the square root of 2,500, 12,500. It's about 111. And so see, if you take here near the middle, and you go up 111 once, twice, you're most of the y range. Or start here in the middle and go down 100 and another 100. That's most of the y range. Right? So 111.8, right, that is a standard deviation. Square root of 12,500, 1.8 or so. And in linear regression, we often ask, is this a strong relationship? Right? Is the relationship between y and x very strong? And one thing that gets computed in this is something called r squared, which basically is 1 minus the variance of y given x over the marginal variance of y. And this r squared thing is between 0 and 1, where if there's a perfect linear relationship, and once you know x and there's no variability of y and everything's perfectly on that line, right, then it's 1. If there's no linear relationship and it's just complete random scatter, unrelated totally, or nonlinear, then it's down at 0. So in this case, right, it's 1 minus the conditional variance was just related to the errors. Right? If you know its position on the line, then the only variability is how far away are you. But marginally, right, it's not conditioned on x. There's more variability because there's a part that's due to the x's and the regression line, and there's a part due to the random scatter about the line. In this application, this was 50 squared over the number we got there. So it's about 0.8875. Right? A correlation like that is pretty strong for most things. In physical sciences, doing balancing equations, reactions and things, it might be quite a bit higher. Some natural resources things could be very high. A lot of social things can be very, much smaller. Right? So it's pretty realistic, and it shows up in our plots. This correlation between these points is about 0.48 or something. In our actual example, it's just to finish, give a number with this. The correlation between our x and y values, 0.88, just about what was predicted by the model. Yes.
Is it like closer to 1 is more correlated?
Yep. So when we had the picture, that's correlation of 1. Because then there's no variability off the line, right? Sigma squared error, there's no error here. So that would be 0, right? So if that's 0, right? That it's just perfectly on the line. So this was a a little more involved example to, we have this relationship. The second important relationship is this variance, conditional variance, right? But these two relationships, not only in this example, but can be used in a lot of other things, right? So like the medical, right, example, right? So if you have n subjects, and you're doing a binomial experiment, and P is the probability of success. So that X, given its probability, is binomial. Then conditional on that probability, but based on the binomial distribution, we know things about mean and variance. We know that the expectation of X given P is n times P, and the variance of X given P is n times P times 1 minus P. Those are relationships just from the binomial distribution. We looked at those as direct computations or deriving from the moment generating function or things like that. But across hospitals, you get different P's, right? You get different proportions, right? So if you're taking sample from different hospitals, what's the distribution of X that you're likely to have? Well, that implies that P might have a distribution, right? And so mostly we talk about P as a parameter, as a number, but if every hospital has its own value of P, you can think about P as a random variable. Right? Pick a hospital, it has a P. Right? So we can give a distribution to it. In Bayesian thinking or probability thinking, anything that you don't know, you might give a probability distribution to. So we could say that P has a beta distribution, as one example, with a couple of parameters. So beta has values in P between 0 and 1. So 0% of the women have P oddities, 0% to 100%, somewhere in there, right, is it possible. For a beta distribution, right, we know some facts. That the expectation of P, whatever the random variables, we take expectation of that. It might look a little bit funny because usually that's a number, but we're thinking about it now as a random variable, right? Because different P for every hospital. The average, right, is alpha over alpha plus beta. And the variance of P, right, is alpha times beta over alpha plus beta squared times alpha plus beta plus 1. So let's say you take all these different hospitals and you take the first 100 women, or say the first 40 women in each hospital, right? That comes in and has a birth that's a non-cesarean birth, right? With other restrictions, so that the type of individuals that they're studying in this report that they're working on, that they qualify to 40 per medical center. Right? What's the expected number and what's the variance of the number who have episiotomies? So what is expectation of X? What's the variance of X? So we can say N is 40 per hospital. And there's some, and then we're going to count the number. Well, according to the professor in graduate school who called this Adams rule, and he called this one Eve's rule, because the variance one is EBBE, so, I don't know, something to just remember, right? So the expectation of X, the number, right, is the expectation of conditional expectation, but it's P here, right? In this application. So the expectation of X given P is for binomial is n times P. And so it's n times the expected value of P across the distribution of hospitals. So it's going to be n times alpha over alpha plus beta. So that's the average value of X. Kind of the average rate across hospitals for the proportion times the number that's in. Assuming that there's a constant number. You can adjust these things if there's different rates by different hospitals. But so what's the variance though? I'm going to put it on the next page. And just, but any questions about what's the variance? What's the variance of X? It's the expectation of the conditional variance plus the variance of the conditional expectation. So the variance of n times P times 1 minus P, the variance of X given a certain value of P is that, and then the variance of this thing is n times P. So I'm going to take the n out and break this up. Expectation of P minus expectation of P squared. There. The n is a multiplier, so I'll just run out of the variance of P. The expectation, so it gets kind of a little bit messy. So this thing, right, is alpha over alpha plus beta. This is the variance formula that you would put in there, alpha plus beta squared, alpha plus beta plus 1. This expectation of P squared, the expectation of P squared is the variance of P plus the expectation of P quantity squared. So you put those two formulas in there to figure that one out. And that would be the, actually the variance X. So in comparison to just a single binomial, we have more variability. Because there's a variability not only due to the binomial nature of the observation, but because the hospitals have variability. Right? So both of them get added in there. This one's a little bit messy to write out the final answer. So let's look at one more example. Right? So we could have some count the number of cases of having triplets or more, right? By counting, right? There's kind of rare, right? There are not many triplets. There's twins. There's fewer triplets, right? Sometimes you have more. Right? So X number of births in a year that are triplets or more. And so lambda is going to be the rate. It's kind of rare. You would define this on some certain population, right? Say a population of say 100,000. It's kind of small, still a small number. You don't see that many. Right? So you might say that this thing has a Poisson distribution. So the probability that X equals some number has a Poisson probability. So, lambda to the K, either to lambda over K factorial, K, nav, or the integers. That might be a reasonable if lambda is the rate. But now we're going to look at this at a whole bunch of different areas, right? Or a whole bunch of different subsets of the population. I try to make it kind of equal at 100,000, right? So there might be different regions of Vermont, different regions of New York, and so on, and kind of divide counties up so they get kind of equal population size. Kind of possible, right? But there's variability in lambda. So there is variability in lambda across areas in reality. What's a model we can use for lambda? How can we give probabilities to lambda? So lambda's really a number greater than 0. All you're going to pick one of our distributions that has support on the positive real line. One option is a gamma random variable. So that had support on the positive real line. It's very flexible. You can match mean and variance. It's kind of skew. So there's areas with a lower rate. Why would different populations have different rates of having triplets? There is clustering of the population by race ethnicity. Certain race ethnicity groups are a little bit more likely to have triplets or multiple births. There's also clustering by ages, a little bit. Some populations in certain areas are having children at older ages. That's kind of associated with multiple births. Using IVR, in vitro fertilization, is associated with multiple births. Those rates differ across the country. So might not be a lot of variability, but there's going to be some. Right? Some medical centers might specialize in issues of pregnancy and conception, right? And so then they would have more local people. If you put in a center that specializes, then maybe more people are willing to do it if they just have to drive a short distance. If you have to travel, 2 states over to do it, it's a different thing, right? It's a bigger expense, more inconvenient, right? So there could be some variability for a number of reasons like that, right? So the expectation. Now lambda we thought about as a number, right? But now I'm treating it like a random variable because it differs by area, right? Because it's different by area, it has variability. I can put a distribution on it and think about that to describe the randomness. This average is alpha times beta, and the variance of lambda alpha beta squared. Right. So out of an area, what's the average value? What's the average number of births that are triplets or more? What's the variability of x? What's the marginal? So expectation of x and variance of x. What's the expectation of x given lambda? So you can think about the model for x with a certain rate, and then you can think about the distribution of rate. So it kind of breaks up your thinking to thinking about 2 different pieces of the puzzle. What's affects randomness? So there's kind of that advantage. So this is just lambda. Poisson's real simple. So it's alpha times beta. The variance, what is it just going to be the variance? It's going to be alpha, beta. There's a square up there that I can't quite see. Right. That's the variance. So anyway, so a Poisson, a single Poisson, its variance, if its mean was alpha beta, its variance would be alpha beta. Right? What happens here? How do we get more variability? Well, there's the expectation of the conditional variance plus the variance of the conditional expectation. So this is just lambda. This is just lambda. Poisson is kind of simple like that, right? I don't know if I wrote those. Right? So Poisson, the expectation of x given lambda is the same as the variance of x given lambda. It's just lambda. They're the same. Very special. No other distribution has that. So it's the expectation of lambda plus the variance of lambda. The expectation of lambda is alpha beta. And the variance is alpha beta squared. So it's going to be greater than the mean, right? So the variance of x is greater than what you would get from a single Poisson. There's this extra variation. That's in there. So as they go, USA Today goes in and collects all these data, and they look at rape, kind of standardize them for 100,000 people, and they are very likely to see more variability than just a single distribution. They can have this kind of mixture of distributions that's there. Yeah.
Could you just briefly go back to the bottom of the
Previous one?
Yeah.
Right, so I didn't write out all these different pieces, right? But this binomial, because the variance was p times 1 minus p in there, and it makes it a little more complicated. Right? But this conditional thinking helps solve a few other types of problems, right? We'll look at step 1. Right?
Yeah, thank you.
Right, so let's say you have a company, and you get in customers per day. And that's random. So n is distributed as a Poisson with a rate of 50. On average, you get 50 customers per day. The standard deviation, so the square root of 50 is about 7. So 50 plus or minus 7, 50 plus or minus 14 is kind of typically what you get at a store. Right? And let's say x of j, x, right, is x of j is the number of bottles of water bought by customer j. Right, and that's also Poisson. So x of j is Poisson 1.5. Imagine your store, you're a street vendor, you have people coming by, usually have 50 people on average buy from you in a given day, and the people buying buy 1.5 bottles of water on average. How many bottles of water do you expect to sell? What's the variance of the number you sell? So we're interested in that, right? So this is total, total water bottles sold. You want to have enough on stock so you can sell to everybody, right? But you don't want to have too many there because it's harder to move around if you have way too much. Right? You want to come pretty close to selling out every time. What's the expected number? This is a little complicated. It looks complicated because n is in there, right? N is random, right? You're having something random in a summation or something like that actually is, just dealing with it by itself is kind of messy, right? You could, dealing with it directly, you'd have to have the joint distribution of n and x, but the x's, well, in any case, conditioning is helpful. I'll call that sum. I'll call that s for the sum. So what's the expected value of s? Right? Condition on it, right? We can take the expectation of this thing, j going from 1 to n of x of j, given n, right? If we condition on having n people, right, then that thing becomes more of a regular sum, right? Just the indices become fixed numbers. Right? Assuming you have n people, what's the expected value? There's n people, and they do 1.5 on average. And you're going to get 1.5 times n as an average. But n, we had a distribution for the number of people as 50, Poisson 50, so it had an average of 50. So this is 1.5 times 50, so we get an average of 75 bottles of water on average. What's our variability? What's the variability of that sum. I'm going to use S again, so I'll just write sum. Expectation of the variance of this thing. Plus the variance of the expectation. Now we did this one already. The conditional expectation here was just 1.5 times n, because it's 1.5 for each x, and there's n of them. Conditional on n, we can just write n there. What's the variance of the sum? Well, if we assume that each person coming up, or each group coming up, is independent of each other, then we would just get n times the variance of each one. Well, there's n of them. Each one would have a variance of 1.5 because it's Poisson. Yeah, so there's 1.5 for each x. There's n of them. They're independent, so we just add the variance. So it simplifies like that. So the expectation of n, again, is 50. That's 1.5. This one, 1.5, is a constant in this variance term, so it gets squared. The variance of n, because it's Poisson, is 50. And so that ends up being 75 plus 112 plus 50, which is 187.50 as a variance. The standard deviation is the square root of that. So what is that square root? The square root of 187.5. It's about 13.7. 13.7. So how many bottles of water do you want to bring with you? If you take, this is adding things together. The Poisson itself is not quite normal, but a normal kind of approximation, the mean plus or minus a couple standard deviations is going to cover most of your range. Right? So particularly if you take the mean and you add a couple standard deviations to it, 75 plus about 14 plus another 14 plus about 28, so 103 bottles. So if you have 110 bottles, you're probably going to cover all your demand most of the time. But anyway, something that was, figuring out what is the expectation of this thing directly. It seems kind of you have these two different distributions to get together. They're related somehow, kind of in a complex way. If n is 1, you get 1x. If n is 2, you get 2x's. If n is 3, you get 3x's. So it's kind of a nightmare to write down the actual distribution of that thing because of the kind of way it grows. But with conditioning and these two relationships, is pretty fast to get those mean and variance, right? But any questions about it? So anyway, this thinking about like a measurement that you're going to have, and then how do the rates come from an area, gets used in areas, sometimes these are called hierarchical models. You have kind of the individual measurements and then rates that are at another level. And if you can think about what affects things at both levels, you can kind of break up the problem into more manageable And these things, instead of just 2 levels, really things can go to multiple levels. If you're thinking about children in schools, right, and maybe the distribution of, students that have individualized education plans, so special needs children or children with any type of, emotional, learning, other identified needs, right, in a school. Well, there's children in the schools, they're in classrooms, those are inside of schools, those are in districts, those are in states. And so all these are hierarchies that are there. And certain things affect, when you're modeling, affect those different things. So it might be hard to think about overall what the distribution of some of these things, but you might get something out of thinking about these different hierarchies that are there. Sometimes these are hierarchical models. Sometimes when it's 2 levels like this, these are sometimes called mixture models, because it's like a gamma mixture of Poissons or a beta mixture of binomials, right? Kind of mixing these things together. There's an area of statistics called small area estimation. It's particularly used with surveys and government statistics. So you don't want, we get estimates of poverty or unemployment overall in the United States, maybe even by state for some of the big states. But you really want it by county. Right? So you have all these small areas. And so the small areas in the counties within a state have a similar unemployment rate or poverty rate or housing rate to the state. Right? But there's variability. So you can have all the people that live there, the percent of adults that are in the labor force and employed, and then there's kind of state level aggregates, and then county level, and then the individual people. So these type of models get used in that, and these relationships of the marginal to the conditional is very useful, for thinking about that type of thing. So that brings us really to the third main point is Bayes calculations. And this is kind of related to 6.8 in the book on compounding. Kind of does this thing where you take a mixture of things and do what we did with looking at applying those 2 things. So there's an example there. It's not exactly what we're going to do, but it's very much related, right? So we've used Bayes' rule, kind of in more elementary probabilities. We had a tree. We had a couple of events. We had a probability of A, and then the probability of not that was 1 minus the probability of A. And then some of it conditional on A, we had B or not B to draw out a simple 2x2 tree. And so we had the conditional probabilities, the probability of B given A, probability of not B given A, probability of B given not A, and 1 minus that is probability of not B given not A. So those kind of 4 conditional probabilities. And then in Bayes' rule we asked, well, if you know B, suppose you know B, what's then the probability of A? How does that new information, if you know B, how does that update your information about A, right? So these were like disease rates, maybe there's 3% disease rate, and now you've done testing for people. If this is the prevalence is about 3% or 30% or whatever it was. Once you know that somebody tests positive or they test negative, how does that change the probabilities, right? And that's how we updated probability. So the formula we have here, one way of writing it was the joint distribution of both of them, right, over the marginal of B. Right, so the joint probabilities over the marginal one that we're assuming that we know. And so it was a probability of A times the probability of B given A, right? We can write the joint as the probability of one times the other, and if we're told the things to make up those, we're told that. probability of B is that joint probability with integrating out A. And in the simple case, it was an addition where you either had B with A or you had B with not A. So that's we called that one a rule for total probability in there. And so that's how we did that. So we get new probabilities out of it. We can do this with probability densities and probability distributions too. And instead of having just a number here for one of these probabilities, if this is a density, marginal density for a random variable, and this is a conditional density, the same updating and transformation going to reverse conditioning also works. Right? So kind of in our hierarchical models, it's very normal to state things about the rate of disease or rate of treatments, how it varies across counties. And then for a certain number of people, have binomial. Well, once you see the number of people, we're going to ask what was P, what was the proportion. So we're going to reverse it. So, we're going to do the same thing. So say X. We'll look at one example here that's doing beta binomial, right? So P is proportion. It's a beta distribution with some proportions, alpha and beta. And then X given P for a certain sample size is going to be binomial. So a priori, we have some opinion about the rates of things going on. So, a priori, without seeing any data, or any new data rather, right? Before seeing data X, before seeing counts of measurements, have some prior information, based on historical studies. If you work in the field, you see this in hospitals, you see rates and things like that. So let's say that we have a beta distribution that's something like 12 and 8. Like 8 and 12. I want to do 8 and 12, right? Well, the expectation before you see any data is 8 over 20 is about 0.4. 40%, you can figure out what the variance is. That's not a lot of information, but a priori you have an idea of maybe what the average variance is, right? So we had homework problems for binomial. We had a mean and variance. You figured out what alpha and beta were for that, right? And then you have some data, right? So X comes in, we observe X. Maybe we have 40 cases, and we want to say, maybe we observe that X is observed. So 40% would be 16, but maybe we only have 10. We observe this. So the Bayesian calculation then is what's the distribution of P? What's our information about the true rate P given our data? That is, what is P given X? This is called the posterior. If we can figure out what distribution this is, right, that's called the posterior distribution of P given our information given X. That is, just like in the 2x2, the tree thing, as we updated probabilities, we want to update distribution to reflect new information. So how does it work out? Any questions? No? Is that out? So we want the density of P given X. So it should be a joint density of P and X over the distribution of X. And I know that one of these is continuous and one is discrete. It's going to work out. Right? It's about just got to use unified symbols to not make it a little easier. The numerator, we had a density for that, and then a density for X given P, which is really a probability function. We're writing the joint as a marginal times a conditional with a reversal back to what we can model. Right? We can model a binomial with that. Think about that. The marginal in X really has the same thing here, but to get just the marginal of X itself, we integrate out P. The corresponding thing with the tree is we added over the cases where you have either A or not A. Like we took all the different possibilities for A and averaged over them. Right? Weighted by the probability of the A here, we have the density. So what does this end up looking like? Right? If we do this for, if this one is beta and this is binomial, right? We get a formula here, so leave a little bit of room. Right? Alpha plus beta, gamma alpha, gamma beta. And this one had P to the alpha minus 1, 1 minus P to the beta minus 1. And then the binomial one, if there's an n choose x, P to the x, 1 minus P to the n minus x. And the denominator is going to have that same thing up there, but integrate out P. All right, so this first part is the density of a beta distribution, and that's a binomial. And if you integrate P out of that product, you're just left with X, the distribution of X. Right? So it looks messy, some things cancel. There's these gamma functions up here also are down here. They don't involve P. Right? So that goes away. Right? What else cancels? Yeah, n choose X, right? So that doesn't involve P, it's down here. 2, that would cancel. Right? Once you cancel f of P given X, you're going to end up with P. You're just going to have the P and 1 minus P terms that are left, right? And those we can simplify a little bit. Right? We can combine the P powers and the 1 minus P powers in there. All comes down to alpha plus X equals 1, 1 minus P to beta plus n minus X minus 1. There's an integral. P, its range is 0 to 1. P alpha plus X minus 1, 1 minus P beta plus n minus X minus 1 P. So that's the simplification. The thing that's in the denominator is the thing that you need to divide by so that the numerator integrates to 1. And in fact, this thing is called a beta integral. It's related to the gammas. This looks like, what does this look like? You have a P and a 1 minus P. You have a range going from 0 to 1 of that. It looks like another beta. In fact, it is another beta. That this thing would simplify alpha plus beta. I know it's a big jump to just write this down, but this is what it is. Right? The gamma of the sum of those things, the alpha plus X, beta plus n minus X. And there's the gamma of this first part, gamma of the second part, and we get the p alpha plus x minus 1, 1 minus p to beta minus x minus 1. So p given x turns out to have another beta distribution. Right? That's related to both our prior numbers, alpha and beta, that we chose based on our knowledge, our prior input, and then the data x that we get from our experiment. Right? So lo and behold, through all this, p given x turns out to have a beta distribution. Alpha plus x, beta plus a minus x. And this is called the posterior distribution, like I mentioned. So that's going to be a probability distribution. And that's going to can be for Bayesian approach, describes the inference that we would give for saying what we think p is. That's the distribution. It has an average, it has a variability, it has a whole shape of the distribution and where the likely values are. Right? We can calculate percentiles, and that's how we would say things about this. So in particular, so let's see, for our example, p, I said was beta, 812. So the expectation of p a priori, 8 over 8 plus 12, 8 over 20 was 0.4. We had 40 cases and observed 10. P hat is often a symbol used for just the sample proportion. So in the sample, that is 0.25. Right? So it's a little bit lower. Our sample proportion is a little bit lower. So given our expert opinion that went into our prior distribution and these new data, how do we summarize the evidence about it? A Bayesian statistician would look at this conditional distribution. It's going to be a beta distribution, just 8 plus 10 here, and then 12 plus 30 here, so 18 and 42. So the conditional expectation of p given x, since it's a posterior distribution, this is called a posterior mean. Posterior average after, posterior or after seeing our data, right, is the 18 over 18 plus 42, so 18 over 50, 60. That into 6 goes into both those things, so 3/10. That's nice, that works. So yeah, 30%. So our a priori, we thought it would be about 40%, but our data was a little bit lower at 25%. If you combine these things through this Bayesian way, you get a posterior average, a conditional expectation of 30%. So that's one way to do actually statistical inference, right? To summarize things based on about these unknown values of p across the region, right, for this particular one. You could also do the posterior variance, right? One thing that's going to happen is you get bigger and bigger samples, variance goes down as you get bigger totals here, right, for the beta. So as you get more and more evidence, that posterior distribution is going to get tighter and tighter around a certain range of values of p. Right? So in government statistics, they have prior distributions, and every single area gets its own value of x. Every single area gets its own posterior distribution, and so you get to do inference for all the different counties. Right? Some of them are based on small sample sizes. You don't necessarily have that much sample in every county, but the bigger counties have big sample sizes, so they have smaller variance. And so it kind of naturally reflects that. But in principle, this can be done with any pairs of distributions, right? Continuous or otherwise. You didn't have to choose a beta or binomial. You can choose different things. depending on how your data is collected and things like that. But still going through the same calculation gives you this inference. But any questions? So the homework that's due on what's on Thursday, I know it's a little short time frame given that we came back from that, really concerned kind of previous stuff. So some of the work with conditional densities and doing the marginal and things like that will be useful in that. There's a bit that's in that. Anyway, okay, we'll stop there for now. Bye there. And yeah, so we should need to talk about advising about class. My meeting with another student right after, as it is, but think about your schedule. Thursday afternoon, or sure that should be fine. Okay. All right. Yep. Good. Yeah, I'm going to see you. Yeah. Yeah, bye.
Well, that's not very Let me know what you don't get. Everything. Okay, that's too much. Started my draft.
Yeah, there you go.